Hi, my name is Victor Kai with John Kraft from Analog Devices, and our project is on channel leakage cancellation for SDR narrowband radar interferometry using GNU Radio. So first, some background. A traditional distance sensing pulse or FMCW radar requires an ultrawide bandwidth of around 1 gigahertz in order to measure around 15 centimeter resolution in distance sensing. However, for emerging SDR technologies with limited bandwidth, such wide bandwidth is not feasible for our distance sensing radar. So in last year's project, I got around that by developing an MFCW radar. MFCW stands for multiple frequency continuous wave. I used two different frequencies of CW waves with slightly different frequencies. And when those reflect back from the target, they each come back with a phase offset. And the phase difference between those frequencies is used to determine the distance of the object. However, in last year's project, the distance sensing accuracy was limited by the leakage from transmitter to receiver as integrated in the same SDR module. So this year's major improvement was in the distance sensing accuracy by introducing a software-based leakage cancellation. Now there are two main types of leakage. First, we have cross-channel leakage, in which the leakage is occurring between two different channels between the two different SDRs. And the second one is a single-channel leakage, where the transmit of the same SDR is leaking into its own receive within that SDR. So these are the two types of leakage that we will be dealing with in this project. So here's how I have my system set up. I have two SDRs for my two-channel MFCW radar. I have 4 antennas, 2 for transmit, these transmit tin cans, and 2 for receive, these panel antennas. And then for a distance sensing test, I have this slider track, the camera slider rail, with a sliding target of aluminum foil. The track is ruled so I can set the target to a specific distance, and then I can compare the radar measurement with the actual distance. For a Doppler speed sensing test, I have this fan which I covered in metal tape to simulate a moving target. So here's my GNU Radio Code for my MFCW software setup. We have 2 channels, channel A and channel B, at 2 different frequencies, the transmit and receive, and then each of these gives a phase offset, and we can use the phase difference in order to calculate the distance. And then we also have a speed sensing portion which taps off of one of these channels and measures the Doppler frequency shift for the speed. We can also see here the GUI interface, which includes visualization for the 2 channels waveforms and phases, also a histogram for the distance points, and a waterfall view for the Doppler speed sensing. To test the radar accuracy, we moved the target in 1 centimeter increments and then made a measurement each time and produced a plot like this. Here in the plot, the x-axis represents the actual target distance, while the y-axis represents the distance measured by our radar. This green line here is when the measured distance is exactly equal to the actual distance, and so ideally everything should be along this green line. So originally we were using a direct linear phase subtraction to get the phase difference, and that produced a plot something like this. where most of the points would be along the green line. However, we see some of these points will actually end up in the negative distance range, which we don't want. And this was because of the direct linear phase subtraction. Each of these phases, the phase for each of these channels, comes in from negative pi to pi. And when we directly subtract them, the phase will be anywhere from negative 2 pi to 2 pi. And so these negative phases here will give us erroneous negative distance measurements. So we need a more sophisticated algorithm in order to correct this erroneous output. So here is our algorithm for correcting the erroneous output. We have a multiply conjugate to subtract the phases in this e to the I phi form so that the phases won't go outside of this range. We can transpose by 2 pi and use a modulo in order to make sure that all the phases end up in the 0 to 2 pi range, and so all the distances will end up in the correct 0 to 150 centimeter range. That will translate into a GNU Radio plot that looks, or code that looks something like this. We have the two signals here, and we can use in the e to the I phi form, we can use a multiply conjugate to subtract their phases, and we can add 2 pi and use mod 2 pi to ensure that everything is in the right place. So if we move up to this top right chart here, we can see that all the points now lie close to the green line, and none of the points gave us a erroneous negative distance. This gave us a 25 centimeter distance sensing accuracy, which is pretty good. But we do see a slight problem here where there's this periodic oscillation, this sinusoidal systematic error that is occurring. And we will be attempting to use leakage compensation to flatten that out. So here's how we simulated the impact of a leakage signal using the GNU Radio Companion. So we added a portion into our code where we're injecting an adjustable percentage of transmit leakage into each receiver. So we're taking this transmit signal and adding a adjustable percent of amplitude and the adjustable phase of it, adding that into the receive in the simulation. And then we can plot that and it will give us something like this, where we can see the same signature sinusoidal-like shape to the error. And so this, these simulations, adjusting these parameters, we're not only able to have confidence that the error that we're seeing in the previous slide was a leakage issue, but also be able to estimate how much leakage there is in each of these channels. So here are the techniques we use to actually implement a leakage compensation. So we add an open air leakage calibration step where we remove the target. And when the target is removed, we can see here in this diagram, the transmit signal will transmit into open air. Basically, it won't come back. And all that the receiver will see then is only the leakage from that transmit into the receive. And this is exactly what we're looking to cancel out. So with a similar technique as the last slide, we can take a bit of the transmit and adjust these parameters and then add that into the receive portion. And basically adjust these amplitude and phase parameters so that this transmit can exactly cancel out the leakage, and then we don't have to worry about that. So we do that for both channels, and we'll get a result something like this. The red line here is the transmit, the blue line is the receive, and the green line is the leakage compensation. So by applying the leakage compensation that is equal to the negative of the leakage image, we can make the receive side flatline, which is exactly what we want. We don't want to be seeing any of that. That means that we successfully canceled out all of the leakage. Here's a test we conducted to quantify the amount of leakage. In this case, after we do the leakage calibration from the previous slide, we can add back the target now. And so that adds back this reflected signal from the transmit into the receive. And then we can actually compare the receive signal with the leakage image. So again, in these charts, the red is the transmit, the blue is the receive, and the green is the leakage compensation. In this case, for the blue, the receive signal is entirely the reflected signal, as we have already canceled out the leakage image. So we can compare now the receive signal and the leakage. The leakage is 20% of the amplitude of the receive signal in channel A, and then is 45% in channel B. So you can see that there is a significant leakage that is detected, as much as 20 to 45% of the amplitude. And this explains why leakage compensation is so necessary to achieve accurate phase measurements. Now this was a single channel leakage. In this project specifically with MFCW, the cross channel leakage is actually negligibly small, as each SDR is on a different channel. They're each transmitting and receiving different frequencies. So that cross channel leakage is minimized. So the dominant leakage here will be the single channel leakage from transmit to receive within the same SDR. So here are the results of the MFCW radar distance test after the leakage compensation was applied. Here we can see that the open air leakage calibration successfully flattened out the leakage signal. This Rx is flattened out to 0. And this chart on the right shows the data. With this leakage compensation, the distance sensing accuracy was significantly improved from 25 centimeters to 12 centimeters. As you can see, all of the points lie closer to this green line than before, especially in this near end range below 50 centimeters. We have actually an accuracy of single-digit accuracy below 50 centimeters. So there is a significant improvement in the radar accuracy thanks to this leakage compensation. So here's a better visualization of the before and after of our leakage compensation. Again, on this chart, the actual target distance is on the X, the measured target distance is on the Y, and this green line represents that the measured distance is equal to the actual distance. That is the ideal. We can see that the gray line here is without the leakage compensation, and the red one is our data from after we did apply a leakage compensation. And noticeably, the red line hugs this green line a lot closer than the gray one, especially in this below 50, this short range area. It's flattened out these humps significantly and has done quite a bit in flattening the later humps as well. So our leakage compensation is definitely working. So in addition to improving the radar's distance sensing portion, we also implemented a velocity sensing portion, which in MFCW comes practically for free, as our velocity sensing with Doppler only requires a single CW wave. So you can just tap off of one of the MFCW channels and then find the frequency shift for the Doppler. So in our case, we're using a fan here in our setup. We're using a fan with the metal tape on it, which emulates an object of a constant velocity that is either moving toward or away from the radar. And how the fan works is when the fan is blowing away from the radar, then this frequency shift will be negative as the fan blades are quote-unquote moving away from the radar while they push the air forward, or I should say away from the radar. And on the other hand, if the fan is turning such that the air is pushed toward the radar, then these fan blades are also moving quote-unquote towards the radar, so that Doppler frequency shift will be positive. It will increase the frequency. So we used an FFT and a waterfall format to display that. In this waterfall format, the FFT of these frequencies is the frequency offset is shown on the X, and then each of these FFTs is pushed upwards as new ones are created, so we can see backwards in time. So starting a while ago, we see that the fan was turned on to half speed, which gives us a frequency offset of 56 Hertz. When the fan is increased to max speed, the frequency offset is now 84 Hertz, which is about 5 meters per second, the fan speed. Then the fan is stopped, so the frequency offset drops to 0. And finally, the fan is turned around now so that it faces away from the radar, which gives us a negative Doppler frequency shift. So our radar is able to detect not only the fan speed, but also the fan direction. So in conclusion, this project demonstrated that distance sensing is indeed possible using very bandwidth limited low-cost SDR. And our MFCW radar was able to achieve the same 12 centimeter resolution as a traditional radar while using 5 magnitudes less bandwidth, using only a few kilohertz instead of 1 gigahertz. We faced a challenge in the phase measurement accuracy due to inevitable leakage from transmit into receive within the SDRs, creating unintended distortion in the phase measurement. We were able to simulate that in GNU Radio and then create a new algorithm for leakage cancellation by applying a negative image of the leakage signal in GNU Radio and successfully enhancing the radar distance sensing accuracy to 12 centimeters that is comparable to the wavelength of the 2.5 gigahertz signals that were used. As for acknowledgements, I was fortunate to have found a co-op position under the great mentor John Kraft at Analog Devices. He saw my paper last year here in the GNU Radio conference on my dual SDR MFCW research, and he guided me to simulate the channel leakage with GNU Radio, and sparked my leakage cancellation idea in MFCW to resolve the periodic variation in the distance measurement. I would also like to thank all the GRC organizers and reviewers for the chance to share my work as a high school student. The issue of channel leakage was actually first brought to my attention in one of the reviewers' comments in my GRC paper from last year, so I'm really grateful for the feedback there. Also, thank you for the GNU Radio community and its collaborative and freeware spirit, which is enabling young radio enthusiasts like me to pursue research and to push innovation forwards. Finally, here are my references. I would like to thank you all for listening to my talk. If you would like more details on my project, you can find them in my paper as in the proceedings. And I hope you guys have a great rest of your day.